Absolutely, yeah. So I guess the sort of the first question is why optimize? Why is this even interesting? Um, and ultimately, I think it has to do with people, with users. Users tend to get annoyed if things are slow. Um, and we can quantify this. So, for example, Google found that if they had half a second extra on their search page time, that translated to a 20% drop in traffic. Um, Akamai found that if they had an extra 100 milliseconds of latency on page load, there's a 7% lower conversion rate. So really, if things aren't fast, people get annoyed and then they don't give you their money. So it's people, it's about people, but it's also really about money. Um, it's really literally about money as well. So if you're doing something like high performance trading, hopefully, if you're doing high performance trading, this isn't your first introduction to Java performance. But what they see with high performance trading is that if they have a 10 millisecond delay in the trading platform, so a really small delay, that translates to a 10% drop in revenue. So potentially millions and millions of dollars. So this stuff matters a lot. But what is optimizing? What do we mean by that? Really, what we mean is make it go faster. But we need to think about it a bit more. Who is it going faster for? When do we want it to go faster? And what are they doing? So these kinds of questions again come back to people. And I think really we can look at this, even though it seems like a really technical subject, applying some of that human-centric design to the technical aspects, those performance aspects, will give us a better answer. Because performance, going faster, it can be a lot of different things. Usually what first when we think of performance is through. So something like how many transactions per second we have. But we should probably also think about latency. So that might be something like startup time. Often it's something like response time, or potentially as well for a long running service, it can be the ramp up time. So it might start quickly, but it might be really slow for a while, which annoys users. We also need to think about capacity. So I always think about capacity a lot when I give an online talk, because of course one of the aspects of capacity is something like bandwidth. Have I actually got enough bandwidth for you to see me? Sometimes I don't. Another aspect of capacity is something like footprint. So that matters a lot in the cloud. How many servers can I cram into a virtualized environment? It can also be something like, well, how much CPU does this service use? If it uses all the CPU on the box, my capacity is less. Using CPU is quite a complicated one, actually, because sometimes it's a good thing, or rather, sometimes using a very small amount of CPU is a good thing because our capacity is higher. But sometimes using a small amount of CPU is a bad thing because it means our utilization is lower. We have this whole server dedicated to the system and is only using 10% of the CPU. The rest of the CPU is wasted. So even for something that's a number, like CPU usage, it can be complicated to figure out, is this a good thing or a bad thing, or what am I actually trying to do? And of course, what makes these things extra interesting and fun is that usually we can't maximize all of them. We can't have something that has really high transactions per second and really low response time and uses no CPU while giving us huge utilization. They go in opposite directions to each other. And sometimes as well, what we think we want isn't necessarily what we want. We need to think about it really hard. And a classic example of that is when we think about throughput. Some systems that are really old-fashioned have really high throughput. And there's a classic quote, never underestimate the bandwidth, by which they mean throughput, of a station wagon full of tapes hurtling down the highway. And this happened because of a real life incident where NASA, they had a data pipe connecting two sites. The data pipe got broken and they needed to do the data transfer. So what they did was they took their physical data tapes, because this was 1981, and they put them in a car and they drove down the highway. The latency was terrible, but the throughput was actually really good. So sometimes you can get to what you want in a way that seems kind of weird because it's got some other performance characteristics that are bad. And of course, to make it even harder, there's no one right answer. The thing that was the right answer a few years ago may now be the wrong answer because requirements change. A colleague told me a story of a bank, and they had this big mainframe, and it was designed for tellers to use it at the end of their shift. So they'd finish their shift, they'd push a button, and it would send one transaction to the mainframe. Next teller would come along, finish their shift, it would send another transaction. But then, of course, this thing called mobile happened. And all of a sudden, instead of one terminal, they had loads and loads of mobile devices, and they had lots and lots of users. And so instead of doing it one person once per shift, these mobile devices were just sending traffic and sending traffic and sending traffic to the server until eventually it said, I am not designed for this, and fell over. And we sometimes say slow is the new down, but of course, down is the worst down. Performance problems become bad enough, the system will go down. And in this case, it wasn't that anybody did anything wrong. It's just that the world changes. And so, as well as requirements change, how technology operates changes. And now, of course, the cloud is a example of this, and it's really rewritten a lot of the rules for what good looks like in terms of performance. Because now, going back to that capacity question, for Java, the smaller we can make our footprint, the better, because memory is money. We need to be thinking about footprint. And this has meant that although some old systems, their performance hasn't changed, how we think about their performance has changed a bit. And among the many roles that I've had over the years, I used to be a performance engineer on the J9 JVM, which is now OpenJ9. And lately, there's a lot of discussion about the performance of OpenJ9, and a lot of people are really happy with the performance of it. And the reason for this is that OpenJ9 has a really good startup time and a really small footprint compared to OpenJDK. The throughput overall, once it gets ramped up, is lower, usually, depending what benchmark you're running. But in a cloud context, things don't tend to stay up for a really long time. Often they don't stay up for long enough to get warmed up. And so then it's that footprint that matters because of the money, and that startup time that matters because you want to think about ramp up time. And we see a really similar story with Quarkus. Although I think with Quarkus, actually, the trade-offs are better. So what we see with Quarkus is it starts up really fast. It has a really small footprint, and it also gives you better throughput than a traditional cloud native framework. So that's kind of win, win, win. And the trade-off is that because it front loads things like reflection to build time, that means if you're using a lot of reflection, you need to do a bit of extra work to make sure that it all works. And I'd heard about Quark. I'm now an engineer on the Quarkus team, but I'd of course heard about Quarkus before I joined Red Hat. And one of the Red Hatters told me a story that I really loved, which is that they were at a conference and they had one of their project managers on booth duty. And so the project manager would demonstrate Quarkus to someone, and then the person would go away, and then the project manager would demonstrate it again. And because they were a project manager, they maybe weren't quite as technical as some of us. And so every time they demonstrated it, they forgot to turn it off again. They forgot to shut it down. And so they looked at their laptop at the end of the day, and they had 120 instances of Quarkus running. But the thing that I really like about this story is that the laptop was fine. There was no ill effects from running 120 instances because, again, the capacity is really good. Quarkus can run in two modes. It can run in JVM mode, where you get really high throughput, really small footprint, and small memory usage, or it can run in native mode, where you get the startup time is I benchmarked it against a light bulb, and it was actually faster than a light bulb. So it's just so fast, it's instantaneous. And so when you think about which you want to use, again, it all depends. It's all these trade-offs. You can run it on native mode where it's built on GraalVM, or you can run it in JVM mode where it's built on OpenJDK. If you're doing something ephemeral or serverless, you want to run it the native Quarkus. But there you do get that trade-off. The throughput usually is a little bit lower. So if you're running your application for a long time, you're probably better off with running on the JVM. When you make these kinds of calculations, it's important to understand how your application will be used, but it's also important to understand how your application won't be used. And this is something that I think most of us have a hard time thinking about. We imagine that we're going to write this application and there's going to be a lot of delighted users who just go, oh yeah, I'm going to use it, I'm going to use it. But a lot of the time, applications get launched and then they just sit and do nothing, or they get forgotten about. So although we would never want to optimize for our application not doing things, I think we do need to think about that. We need to think about how efficient is this at idle, because 30% of virtual machines are zombies doing nothing. And that probably, if you count idle time, that number is much, much higher. So if you kind of know what you want to optimize, how do you do that? The answer is pretty simple. You have to find the bottleneck and fix it. Of course, like a lot of simple things, it's not always that easy. There's a whole bunch of pitfalls that we can experience. The first pitfall is intuition. Ideas are great. Performance optimizing is not the place to have ideas. You need to be guided by the data. So you measure, don't guess. Even if you think you know what's going on, measure to prove it. It's also really important to measure the right thing. And the right thing is the thing your users care about. So if your users care about latency, don't measure throughput. And this leads us to the second pitfall, which is numbers. I think if we measure something and we have numbers, it's really easy to get so convinced by the fact that there's numbers and they look official and clever that we don't think, are these the right numbers? Did I measure the right thing? So I want to explain something that actually comes more from business, but I think it's really useful when thinking about optimizing. And that's the idea of leading indicators and lagging indicators. Lagging indicators are the things that we really care about. How much business is my company doing? How many users do I have? Lagging indicators are usually really easy to measure. We look in our bank account. The problem with lagging indicators is they're hard to change. How do I change how much money I have? Oh, Leading indicators, on the other hand, they're really easy to change. I'm just going to increase my memory by this. I'm just going to, remove this line of code. They're predictive of a thing we care about. If I make this change, I will do better. The problem is they're hard to identify. What's the thing that predicts the thing that I care about? So I did a few little performance experiments to show how sometimes these things can be confusing. Like all benchmarks, treat them with caution. So these, this is not absolute truth. This is just some experiments I did. And they're based on a master's thesis I did 15 years ago on garbage collection. And at the time, there was a lot of really bad advice going around that annoyed me, which said the way to optimize your application is to reduce the time spent in garbage collection. And this is just, it's sometimes wrong, but it's often, it's sometimes right, but it's often just wrong, because investing in garbage collection can be an investment. It can make the rest of your application go faster. So I've just lost my slides, one moment. Okay, cool. So I think we've got my slides back. So what I did in 2007 was I did a little experiment where every garbage collection, I also did a compaction of the heap. This meant that the time spent in garbage collection was really, really high. But if you look at that second chart, you can see that the throughput, the blue line, was actually higher, because doing all of those garbage collections meant that heap was really compact, my memory locality was great, allocation was fast, and so my application overall went better. So I tried to reproduce that application. I used a different benchmark. So I used a benchmark called DayTrader, and then I sent load into my application with JMeter. And then I tried some GC options. So I said, I'm going to compact every GC. That didn't give me quite the result I was expecting, the same result I saw in 2007. So I added a few other options, and then I added a few other options, and then I added a few other options. And none of them actually gave me the same result that I saw in 2007. And in fact, no matter what I changed with the settings, the performance of the application was exactly the same. I should add as well that this is cheating. It's bad science. When you do an experiment, you can't change the experiment until you get the result that you want. An experiment has to be to tell you something that you don't know. But I carried on going, and I eventually found a set of parameters and experiment conditions that gave me the result I was looking for. So here we are. I'm using a tool called GCMV, which I wrote many years ago, to analyze the results. And you can see that in the first case, in my application, it spent about 21 seconds total in GC. So that was 4% of the application time was paused for GC. That's pretty bad. In my second run, it only spent 12 seconds in GC. So that was less time overall. But this is where it gets more complicated. In the first case, the bad case where it spent more time in GC, it collected 24 gig of garbage. In the second case, it only collected 13 gig of garbage. Why did it have less garbage? Because in the first case, the bad case, it did almost 500 transactions per second. In the good case, it did 260 transactions per second. So it did half as many transactions. So of course it had less garbage. So because I was looking at time spent in GC, I actually had the good and the bad cases sort of swapped. So that time in GC, that's a leading indicator. I think it's going to predict the metric that I care about, the transactions per second, which is the lagging indicator. But it may or may not, and it may do it in the opposite way to what I hope. It's also worth thinking about whether these are actually the right indicators. Like, it seems like time spent in GC isn't really a leading indicator at all because it's not predicting it in the way I expect. And is transactions per second actually the indicator I should be caring about? That depends. Maybe I care more about response time. I should also add, what was it that I changed to make the application faster? The thing that I ended up doing was putting JMeter on the same machine, the same laptop as was running the experiment. And it says, no matter what you do, put your JMeter on a different machine. But my laptop, a modern laptop, is so fast, it has so much power, that the network was the bottleneck. And so getting rid of the network bottleneck meant I could then see other bottlenecks. So this comes back to the idea of the bottleneck. You need to be really sure you know what the bottleneck is. Because if you change things elsewhere, you may feel like you're doing less, but it's not actually changing the performance, the thing that you care about. The other thing to bear in mind, the moral of this story, is that time kills all performance advice. So the advice that I had for 15 years ago, isn't the same now. So the full set of morals of the story is that because garbage collection can rearrange the heap, it can actually improve your performance. You have to find the bottleneck, and you have to make sure you've got the right bottleneck. If people give you advice, don't believe them. Validate advice yourself, because time and context and everything kill advice. We see such a lot of performance problems that are caused by advice. And I think, we all know, just because you read it on the internet doesn't mean it's true. And that's extra true for performance. So there used to be this advice that went round that said, if you're programming in Java, make one big method because method dispatching is slow. For Java 1.1, this was true. It hasn't been true since like Java 1.3 or something. It hasn't been true for ages, but it took that advice so long to go away. You still see advice that says reuse your objects because that's going to help the garbage collector because it doesn't have to allocate new ones. Almost always, that advice is really bad. Reusing objects is going to hurt the garbage collection. It's going to make garbage collection worse. And then, of course, we get the classics of, to tune your JVM, use this command line, where you get this sort of folk legend command line. And it's almost always not actually a good one. My colleague Ben Evans, he analyzed a bunch of command lines that had been fed into New Relic. And for some of them, there was obviously typos in the numbers. So there was like these really weird numbers that weren't a multiple of 2 that had been then passed around the internet without people really looking at it and thinking about it and validating it independently. Another piece of advice that you see all the time is use builder. Don't concatenate strings with plus equal. And at that one, actually, it is more or less correct. But even for that kind of bit of advice, you need to think about the context. Because we need to think about, are we actually optimizing or are we micro-optimizing? Jeff Atwood, he did a lovely blog, which I would recommend going away and reading, called The Sad Tragedy of Micro-Optimization Theater. And he looked at exactly this advice. And he did the measurements to see, well, how much difference does it make if I have something as plus equals and I replace it with the string builder? So I thought, I'm going to replicate his experiment. And so I looked through DayTrader, that benchmark that I was already running, and I found some cases where it was using plus equals in a loop. And I thought, I'm going to optimize this and I'm going to see how much difference I get. And so it was the same as before. I ran my experiments. The throughput didn't change. And I thought, what is going on? I eventually worked out the method I was working in was a two-string method. It never got called. So it didn't matter how bad the code in there was. It wasn't worth optimizing, even if the optimization was correct. And we see sort of similar things with, like, in all aspects of our life. So, for example, I fly a lot and I always feel a bit guilty about flying. So instead of taking a taxi to the airport, I'll take public transit. And you may think, yeah, surely this is a good thing. Every little helps. But actually, I spend so much mental energy taking the taxi that there's probably other things that I could be doing that would have a bigger impact. And the other thing about optimizing Java is that our platforms help a lot. So if you have this code, the compiler will turn it into the correct string builder anyway, because the people who write the JVM have far more time to optimize than you do. And so you want to be in a position where you get the benefit of your optimizations by writing clean, typical code. Okay, but what if, despite all that, you really want to optimize? There are tools available that will help. I need those tools because what you can optimize is limited to what you can observe. And Susie, who wrote this, wasn't talking about performance, but it's the exact same thing. You need to be looking at things like observability tools because they're going to give you the insight you need to find the bottleneck. So I've got a little bit of a survey of tools. So there's things like method profilers will tell you where your what methods are spending the most time. You want to look at GC analysis as well, so tools like GCMV. You want to look at the heap, see what's in your heap. Do you want it to be there? And then you can look at a set of suites called application performance management. Those are usually pay for, unlike the others, but they can give you a really good view of the whole application. And then finally, I mentioned observability. The distributed tracing tools, things like OpenTelemetry, will probably give you some pretty good insights as well. Another consideration is that your service is probably not running in a vacuum. It's probably part of a broader system. It's probably a microservice. If you optimize a microservice, is that the optimizing that we said not to do? Maybe, if that service is rarely called. So you need to know the whole system context. How important is this? Is this the bottleneck? Before you decide what to optimize. Just like the bank, where an application whose performance didn't matter turned into an application whose performance mattered a lot. You also need to think about the edges. You need to think about queuing theory, because it's the things that get stuck in the queue, the edge cases, where we see the most horrible performance. And that's something that we need to learn as we grow in our performance optimizing, is to look at the distribution, look at what's going on at the edges. And another way of saying this that Charity Major said is, nines don't matter. It doesn't matter if your average is really good if you have people who aren't unhappy because they're on the edge. And it's not just user unhappiness. In the age of the cloud, if applications are slow, that is money. So I'm really excited by things like Backstage.io's cost optimization, so that we can get those performance financial information available to engineers. So I'm nearly out of time, and I haven't got to the bears yet. The bears is because a while ago, my children, they never ever turn off the TV. It drives me mad. And I eventually snapped. I don't recommend this as a parenting technique, by the way. I eventually snapped. I said, if you leave the TV on when you're not using it, you're a polar bear murderer, because it's just so wasteful to be using energy when we don't need to. And so all of us, for all sorts of reasons, should be avoiding waste. And so optimizing, making things run more efficiently, saves electricity, it saves hardware. And in IT, the data centers that the software we write runs on use 1% to 2% of the world's electricity. That's a lot of electricity. So if we can make our applications so that there's fewer devices out in the world and the hardware has a longer lifetime, we can do that if we have higher efficiency, if we have lower footprint, if we support multi-tenancy in how we write applications. And then that means as well, we should be doing things like optimizing for longevity. Don't plan for obsolescence. Assume things will continue going. And that's going to save energy. It's going to improve efficiency, and it's going to help everything, including polar bears. So to wrap up, optimization is accessible to all of us, and it can actually be really fun. And as long as we're guided by data, as long as we measure, don't guess, and as long as we optimize what matters, we can really make a difference. Thank you.
Thank you very much, Holly. It was really, really useful.
Oh, I think you might be muted, or maybe it's just me who can't hear you.
Oh, one moment, please. Let me check.
Yay! That's better.
That's better. Now you can hear me?
Yeah, I can,
Cool.
yes.
Thank you very much, Holly. It was really interesting, and understanding how optimization could impact your application is really important for every developers and QA engineers, I think, for everyone. And we have some questions. Would you mind to answering them?
Sure. Yeah, absolutely.
Okay. Okay. Good. So, oh, one is really long. Okay, I try to. Sometimes it happens that local testing or even stage shows performance improvements, but on production, due to a big amount of data, we have no improvements or even regression. Was it possible to find such bottleneck issues before production on a small set of data?
Yeah, that's a super question. And we see this all the time. So like we see that if you do a micro benchmark and then you go on your application, you might have chosen a framework and made the wrong decision because the characteristics were different. And then even for the same application with different data in a different environment, the characteristics are going to be different. And I don't know an easy answer to replicate what you get in production in staging. I think what you have to do instead is just make sure that you have that ability to measure and that discipline of measuring at every level. So it's really, I think it's an extension of testing in production, that you are going to see things in production that surprise you. And so you need to make sure that you've got the observability framework in place so that when you get that nasty surprise in production, you can quickly figure out what is it. Sometimes you might be able to then replicate it in staging and make sure that you've got the regression tests. It might be something that just only shows up in production.
Cool. Thank you very much, Holly. I think the next question is more general because people asking, saying awesome talk and thank you. So it's for you, Holly.
Thank you.
And where are the slides available, please? So for participants of this event, they will be available. The records of all speeches will be available via email in a couple of days. So. Thank you very much,
And
Holly.
I've got a website as well. So if you go to hollycummins.com, I've got the slide decks and then the links to recordings as well.
Cool. Thank you very much, Holly, and we really appreciate you being here with us today. So, thank you.
Thank you. Yep, enjoy
Goodbye.
the rest of the conference. Bye.